Hello! In this video we will discuss the concept of conservation of momentum, which is a really powerful tool to have in our toolbox once we understand how it works. In fact, this is pretty much why momentum is a useful concept. First, we need to expand our definition of momentum. Before, we talked about momentum of a single particle. To find the momentum, we simply take that particle's mass and multiply it by its velocity. However, we can also consider the momentum of a group of particles, also called a system of particles. To find the momentum of the system, we simply find the momentum of each particle and add them together. Now, there is a very important rule about momentum that makes all of this useful to learn. If these particles only exert forces on each other and don't interact with anything outside of the system, then the momentum of the system is conserved. What does this mean? It means the following. At some moment in time, which I will call t equals 0, we can have our particles moving around with different velocities. We can calculate the momentum of each particle and add those momentums together and get some number, which I will call c. That value is the momentum of the system at t equals 0. Then, over some stretch of time, let's say 5 seconds, the particles interact with each other, either through collisions or through other forces. Each particle might change its own momentum due to these forces it feels. But if we add up the momentum of all the particles at t equals 5, we will always find that the momentum of the system is the same value as before. This is the conservation of momentum principle. Let's show what this means with an example. Imagine we have an object that is just sitting still. Suddenly it explodes into two separate pieces, and those pieces go flying. Mechanical energy is definitely not conserved. The object started off not moving, so there was zero kinetic energy. After the explosion, the two pieces start moving, so now there is kinetic energy. Nonetheless, since the forces that cause the object to split into two only act between the two objects, the momentum of the system is conserved. So at first the object had a mass of big M, but it had a velocity of 0. Therefore the initial momentum is 0. After the explosion, the system momentum is the mass of A times the velocity of A, plus the mass of B times the velocity of B. Since momentum is conserved, this must also equal 0, since the initial momentum was 0. So the first thing we can tell from this equation, for this to equal 0, the velocities must be pointing in different directions. If they did not, then how could these terms possibly cancel? Mass can't be negative, so that only allows for a negative velocity and a positive velocity. That means that when the object splits into two, the two pieces must be flying in opposite directions. The other possibility is that they both have 0 velocity, but that would be a boring explosion. This equation is also pretty useful because if we know the velocity of one of the objects and the mass of both of them, we can easily find the velocity of the other object. Now, it is very important to realize that this is only true when the only forces that occur are happening between members of the system. If, however, there was also gravity acting on both of these objects, then momentum of our two-object system would not be conserved. However, even in this case, if the gravity only acts in the y direction, we can still consider the momentum in the x direction to be conserved, so we can still write this equation. Now, it's nice that I told you that momentum is conserved, and that you probably believe me, but now I'm going to actually show you why it's true. Let's just imagine a system with two particles, A and B. When A and B exert a force on each other, we have equal and opposite forces. Therefore, we write this equation. The force on A from B equals the opposite of the force on B from A. Next, let's think about the change in momentum of the system. Delta big P is the change in the momentum of the system, and it equals the change in momentum of particle A plus the change in momentum of particle B. Now let's just divide both sides by delta t for a reason that will become clear in a second. Now we know that the change in momentum of a particle divided by the change in time is the sum of forces acting on that particle. In our case, each particle is only feeling one force. So now we can write this equation, where we say that the change in the system's momentum over time is equal to the force that A feels from B plus the force that B feels from A. However, because these two forces are equal and opposite, we can use this equation to rewrite that like this, and we see that the forces cancel. Thus, we are left with a change in system momentum over time equals 0. To make this a bit clearer, we can multiply both sides by delta t, and we see that the change in system momentum is 0. This is the meaning of the conservation of momentum. The system momentum does not change. Now, if there were other forces outside the system acting on any of the particles, this equation would have to look different, since we would have to include those forces here. Those forces probably won't cancel, and so the change in system momentum will not be zero. In summary, we learned that we can calculate the system momentum by just adding up the momentum of all particles in the system. We also learned that system momentum is conserved if the only forces acting on any particle comes from another particle inside the system. This conservation of momentum principle can be extremely useful for problem solving. That's it for this video. Thanks for watching.